A faint glimmer of light reaches Earth after traveling 150 light-years through the void. When astronomers capture that light and split it into wavelengths, they find signatures that shouldn't exist together. Not on one planet, but on 5. All orbiting the same star, all showing traces of water vapor in their atmospheres. This isn't a coincidence or a measurement error. It's a pattern that changes what we thought possible about planetary formation and the distribution of one of the universe's most essential molecules. The James Webb Space Telescope didn't just detect water on distant worlds. It revealed an entire star system drenched in it, forcing scientists to reconsider how common water might be across the galaxy. If you want to follow this discovery as it unfolds, subscribe and hit that like button. Let's explore what Webb found and why it matters. For most of human history, water existed only on Earth as far as anyone knew. Oceans, rivers, ice caps, clouds, all of it seemed unique to our world. Even as astronomy advanced and telescopes improved, water remained elusive. We could see other planets and moons in our solar system, but confirming water on them required missions, probes, and decades of patient observation. Mars showed hints of ancient riverbeds. Europa's icy surface suggested an ocean beneath. Enceladus sprayed geysers into space that tasted of salt. Slowly, water stopped being Earth's exclusive feature and started appearing everywhere we looked closely enough. But finding water in our solar system is one challenge. Finding it on planets orbiting distant stars is something else entirely. Those worlds, called exoplanets, exist so far away that even our most powerful telescopes see them as faint dots if they see them at all. Most exoplanets are detected indirectly through the gravitational wobble they cause in their host stars, or the tiny dip in brightness when they pass in front of them. Actually studying their atmospheres, analyzing what gases surround them, and identifying specific molecules like water requires technology that simply didn't exist until recently. That's where the James Webb Space Telescope enters the story. Launched in December 2021 and positioned nearly 1 million miles from Earth, Webb operates in a region of space that allows it to observe the universe with unprecedented clarity. Unlike Hubble, which primarily observes visible and ultraviolet light, Webb sees in infrared. This matters enormously because infrared wavelengths penetrate dust clouds, reveal heat signatures, and most importantly for this discovery, interact with molecules in ways that make them identifiable. When starlight passes through a planet's atmosphere, molecules absorb specific wavelengths. Water vapor absorbs infrared light in a distinctive pattern, leaving fingerprints in the spectrum. If you collect enough photons and analyze them carefully, those fingerprints become readable. Webb's instruments are sensitive enough to detect these faint signals from planets dozens or even hundreds of light-years away. This capability transformed exoplanet science almost overnight. Instead of merely knowing that a planet exists, astronomers can now ask what it's made of, what gases surround it, and whether conditions there resemble anything familiar. The discovery we're discussing didn't happen by accident. It emerged from a targeted observation campaign focused on a star system known as HD 110067. This system had already attracted attention because transit observations suggested it contained multiple planets. When those planets cross in front of their star, from our perspective, they block a tiny fraction of starlight. The pattern of these transits revealed something unusual. The planets were locked in orbital resonance, meaning their orbits relate to each other in precise mathematical ratios. This kind of configuration is rare and suggests the system has remained stable for billions of years, undisturbed by collisions or chaotic gravitational interactions. Astronomers selected this system for detailed study precisely because of that stability. A calm, organized planetary system offers a clearer picture of atmospheric composition than one disrupted by violence or rapid change. Webb's team scheduled observations during multiple transits, collecting light as it filtered through each planet's atmosphere. The data came back in waves, and as researchers analyzed the spectra, a pattern emerged that no one had anticipated. All 5 planets observable in the system showed evidence of water vapor. Not trace amounts buried in noise, but clear, repeatable signals strong enough to appear across multiple observation sessions. Water was present in every atmosphere studied. This was not expected. Planets in this system orbit close to their star, receiving intense radiation that should strip atmospheres or bake away volatile molecules. Yet water persisted. The implications rippled outward immediately. If water vapor exists on 5 planets in a single system, what does that say about planetary formation? What does it reveal about the delivery mechanisms that bring water to worlds? And most provocatively, if water is this common in one star system, how common might it be across the galaxy? To understand why this discovery matters, we need to step back and examine what water actually represents in the context of planetary science. Water is not just a molecule, it's a marker. It tells us about temperature, pressure, chemistry, and history. On Earth, water exists in 3 states: solid ice, liquid oceans, and vapor in the atmosphere. This versatility makes it essential for life as we know it, but it also makes it a sensitive indicator of environmental conditions. The presence of water vapor in an exoplanet's atmosphere immediately constrains what that world might be like. It suggests temperatures high enough to vaporize water, but not so extreme that molecules disintegrate. It hints at atmospheric pressure sufficient to retain gases against the pull of stellar wind. It raises questions about where the water came from, and whether it has existed since the planet formed or arrived later through comet impacts or chemical reactions. Water also plays a role in atmospheric chemistry that extends far beyond its direct effects. It participates in reactions that produce other molecules. It influences cloud formation and energy distribution. On Earth, the water cycle drives weather, regulates temperature, and sustains ecosystems. Even on lifeless worlds, water shapes atmospheric behavior in profound ways. Detecting it on 5 planets simultaneously provides a snapshot of an entire system's chemistry and history. Scientists can compare how water behaves under different conditions, observe how proximity to the star affects abundance, and test theories about planetary evolution that would otherwise remain speculative. This is why the discovery feels less like a single data point and more like opening a window into processes that govern worlds across the universe. Let's examine the star system itself more closely. HD 110067 sits approximately 150 light-years from Earth in the constellation Coma Berenices. It's a bit smaller and cooler than our Sun, classified as a K-type star. These stars are common in the galaxy and known for their stability and longevity. K-type stars burn their fuel more slowly than Sun-like stars, meaning they can remain stable for tens of billions of years, far longer than the current age of the universe. This extended lifespan has led some scientists to suggest that K-type stars might be ideal hosts for life because they provide stable conditions over immense timescales. The planetary system around HD 110067 contains at least 6 confirmed planets, all orbiting closer to their star than Mercury orbits the Sun. These are not Earth-like worlds in the traditional sense. They range in size from slightly larger than Earth to smaller than Neptune, placing them in a category astronomers call sub-Neptunes. This category is particularly interesting because it doesn't exist in our solar system. We have rocky planets like Earth and gas giants like Neptune, but nothing in between. Sub-Neptunes are the most common type of exoplanet discovered so far, yet we have no local example to study directly. The orbital resonance in this system is striking. The planets move in patterns where their orbital periods relate by simple fractions. For every 2 orbits, one planet completes, another completes 3. These ratios lock the planets into a gravitational dance that has persisted for billions of years. Such configurations form early in a system's history and survive only if nothing disrupts them. The fact that this resonance remains intact tells astronomers that HD 110067 has experienced a remarkably peaceful existence. No rogue planets swept through. No nearby stars passed close enough to perturb orbits. The system formed, settled, and remained stable, preserving the conditions present at its birth. This stability is part of what makes the water detection so significant. If the planets formed with water and retained it over billions of years, it suggests that water can persist even in challenging environments. If water arrived later, the delivery mechanism operated across the entire system, not just on isolated worlds. Either scenario reshapes our understanding of how water is distributed during a planetary formation. Now let's turn to the observations themselves and what Webb actually measured. When a planet transits its star, a tiny fraction of starlight passes through the atmosphere before reaching Earth. That light carries information about what molecules it encountered along the way. Different molecules absorb different wavelengths, creating a unique spectral fingerprint. Water vapor absorbs infrared light strongly at specific wavelengths. Webb's instruments detected these absorption features in the light filtering through the atmospheres of 5 planets. The signal appeared consistently across multiple transits, ruling out random noise or instrumental artifacts. The strength of the absorption varies between planets, suggesting different amounts of water vapor or different atmospheric conditions. Some planets show stronger water signals than others, possibly because they have thicker atmospheres or because water is more abundant in their upper atmospheres where starlight passes through. Analyzing these differences allows scientists to build models of atmospheric structure and composition. One of the planets, designated HD 110067c, showed particularly strong water absorption. This planet orbits close to the star, completing a revolution every few Earth days. Despite the intense radiation it receives, its atmosphere retains significant water vapor. This challenges assumptions about atmospheric erosion and suggests that mechanisms exist to replenish or protect atmospheres even in harsh environments. Another planet, farther out and cooler, showed weaker but still detectable water signals. The variation across planets provides a natural laboratory for studying how distance from the star affects atmospheric chemistry. Closer planets receive more energy, driving stronger evaporation and atmospheric circulation. Farther planets might retain water in different forms or at different altitudes. By comparing the spectra, astronomers can test models of atmospheric physics against real data from multiple worlds. Webb's spectrograph operates by splitting light into thousands of individual wavelengths and measuring the intensity at each one. The resulting spectrum looks like a graph with peaks and valleys, each corresponding to absorption by specific molecules. Water vapor creates a characteristic pattern of valleys at infrared wavelengths. When that pattern appears in data from a planetary transit, it provides strong evidence that water exists in the atmosphere. The confidence level of these detections is high. Multiple observation sessions confirm the signals. Independent analysis teams reviewed the data and reached the same conclusions. The water vapor is real, abundant, and present across the entire observable system. This universality is what elevates the discovery beyond a simple detection and transforms it into a revelation about planetary systems as a whole. To appreciate why this matters, consider what we knew before Webb. Water had been detected on a handful of exoplanets, usually as tentative signals requiring careful interpretation. Each detection was treated as an individual event, interesting but not necessarily representative. The idea that water might be common was suspected, but not proven. Most exoplanet atmospheres remained mysteries, too faint or too distant for detailed analysis. Webb changed that equation by delivering sensitivity and resolution that turned speculation into measurement. The HD 110067 system is not unique or unusual. It's an ordinary star with ordinary planets following ordinary physical laws. If water saturates this system, there's no reason to think it's rare elsewhere. The galaxy contains billions of K-type stars, many hosting sub-Neptune planets in similar configurations. If even a fraction of those systems resemble HD 110067, then water vapor might be one of the most common atmospheric components in the galaxy. This realization shifts the conversation about habitability and the search for life. Water is often called the universal solvent because of its ability to dissolve and transport other molecules. On Earth, life depends on water not just for hydration, but as a medium for biochemistry. Cells are mostly water. Chemical reactions occur in aqueous solutions. DNA's structure depends on water molecules. While it's possible to imagine life based on other chemistries, water-based life is the only kind we know, and it's the template we use when searching for biology elsewhere. Finding water on 5 planets in one system doesn't mean those planets host life. Most of them are far too hot, too irradiated, or too hostile for biology as we understand it. But it does mean the raw material for life is widespread. It suggests that water delivery to planets is not a rare accident, but a routine outcome of planetary formation. And it raises the probability that somewhere in the galaxy, water exists on a world with the right temperature, the right atmosphere, and the right chemistry for life to emerge. Let's explore how water gets onto planets in the first place. This question has occupied planetary scientists for decades because the answer isn't obvious. In the early solar system, the region where Earth formed was hot enough that water would have evaporated. Models suggest that water molecules couldn't condense into solid ice until you moved farther from the Sun, beyond the orbit of Mars. This boundary is called the snow line, and it separates the inner solar system, where rocky planets formed, from the outer solar system, where ice and gas accumulated. If Earth formed inside the snow line, where did its water come from? The leading theory involves delivery by asteroids and comets. These objects formed in the outer solar system where water ice was abundant. Gravitational interactions with the giant planets scattered some of them inward, and when they collided with Earth, they delivered water. Over millions of years, countless impacts accumulated enough water to fill the oceans. Evidence for this comes from isotopic analysis. Water molecules contain hydrogen and oxygen, but hydrogen comes in two forms: ordinary hydrogen and deuterium, a heavier isotope. The ratio of deuterium to hydrogen varies depending on where water formed. By measuring this ratio in Earth's oceans and comparing it to water in comets and asteroids, scientists can identify which objects likely contributed Earth's water. The situation becomes more complex when you move to other star systems. We don't observe the snowline directly, but we can infer where it would have been based on the star's temperature and the system's early history. In HD 110067, the snowline would have been farther from the star than the current positions of the detected planets. This suggests that either the planets formed beyond the snowline and migrated inward, carrying their water with them, or water was delivered after formation through impacts similar to what happened on Earth. Both scenarios are plausible, and distinguishing between them requires additional observations. If the planets formed farther out and migrated, they might retain other volatile molecules beyond just water. Webb's instruments can search for methane, ammonia, and carbon dioxide, molecules that also condense in cold regions. Finding these would support the migration scenario. If the planets formed in place and received water through impacts, the delivery process must have been extraordinarily efficient to supply 5 planets simultaneously. This would imply that the outer regions of the system contained vast reservoirs of icy material and that the dynamics of the early systems scattered that material inward in a sustained bombardment. There's a third possibility that scientists are beginning to consider. Water might form in situ through chemical reactions in the planet's atmosphere. Hydrogen and oxygen are abundant elements, and under the right conditions they can combine to form water. This process occurs on Earth in the upper atmosphere and might be more significant on other worlds. If atmospheric chemistry produces water continuously, it could explain why water persists even on planets subjected to intense stellar radiation. The balance between production and loss would determine the observed abundance. This idea is speculative but testable. By observing how water abundance changes over time or correlates with stellar activity, astronomers can constrain whether in situ production plays a significant role. Webb's ability to monitor planetary atmospheres over multiple years will provide the data needed to test this hypothesis. Understanding water delivery mechanisms has implications far beyond this single system. It informs our models of planetary formation across the galaxy. It helps predict which types of planets are likely to have water and which aren't. And it guides the search for habitable worlds by identifying the conditions necessary for water to accumulate and persist. Now let's discuss the planets themselves in more detail and what Webb revealed about each one. The innermost planet observed, HD 110067b, orbits extremely close to the star, completing a full revolution in just a few days. This proximity subjects it to intense heat and radiation. Surface temperatures likely exceed several hundred degrees Celsius, hot enough to vaporize rock in extreme cases. Despite this, Webb detected water vapor in its atmosphere. The water isn't liquid. At these temperatures and pressures, it exists as superheated steam. The atmosphere itself is likely thick and turbulent, with powerful winds driven by the temperature difference between the day side, which faces the star constantly, and the night side, locked in eternal darkness. How does water survive here? The answer involves atmospheric circulation and replenishment. Even if water molecules are broken apart by ultraviolet radiation or lost to space, new water might be released from the planet's interior through volcanic activity or chemical weathering. Alternatively, the atmosphere might be so thick that the lower layers protect water from the most destructive radiation, allowing it to persist despite the harsh environment. Moving outward, HD 110067 CE orbits slightly farther from the star and shows the strongest water signal of any planet in the system. This planet is particularly intriguing because its position suggests a balance between heat and retention. It's warm enough to maintain a significant water vapor presence, but not so close that all volatiles are immediately stripped away. Models suggest this planet might have a deep atmosphere, possibly with water extending from the upper layers down to a thick cloud deck. If the atmosphere is hydrogen-rich, water vapor could mix with hydrogen and other gases in complex chemical networks. The pressure at the base of such an atmosphere might be immense, creating conditions where water exists in exotic, high-pressure states we don't encounter on Earth. Studying this planet in detail could reveal atmospheric processes that have no terrestrial analog, expanding our understanding of how gases behave under extreme conditions. HD 110067D, the next planet out, presents a different profile. Its water signal is present but weaker than on Planet C. This could indicate a thinner atmosphere or a different atmospheric composition where water is diluted by other gases. Alternatively, the water might be concentrated at altitudes that starlight doesn't penetrate efficiently, making it harder to detect. This planet's intermediate position in the system makes it a key comparison point. By studying how atmospheric properties change with distance from the star, astronomers can identify trends and patterns that reveal the underlying physics governing atmospheric evolution. Each additional planet provides another data point, turning speculation into testable predictions. The fourth and fifth planets, HD 110067E and F, orbit farther still and receive less intense radiation. Their water signals are detectable, but require careful analysis to extract from the data. These planets might represent a transition zone where water vapor gives way to other atmospheric components. Methane and ammonia, which condense at cooler temperatures, might dominate their atmospheres. Alternatively, these planets could retain water in different forms: ice clouds at high altitudes or liquid water droplets in denser lower layers. Webb's observations provide snapshots, moments in time when starlight passed through the atmosphere. Future observations, repeated over months or years, could reveal changes in water abundance tied to seasonal effects or stellar activity. Variability in the water signal would indicate dynamic atmospheres responding to external drivers, providing insight into atmospheric circulation and chemistry. There's also a sixth planet in the system, HD 110067G, which orbits too far for Webb to detect water vapor during the observation campaign. This planet might still contain water, but if it's too cool, the water could be frozen into ice rather than present as vapor. Ice doesn't produce the same spectral fingerprints as vapor, making it invisible to the techniques used in this study. Future observations targeting different wavelengths or different phenomena might reveal ice or other volatile compounds on this distant world. The diversity of water signals across the 5 observed planets is as important as the detection itself. It demonstrates that water's presence and abundance depend on local conditions. Planetary mass, atmospheric thickness, stellar radiation, and distance all play roles. By comparing the planets, scientists can disentangle these factors and build comprehensive models of atmospheric evolution. This comparative approach is powerful. Instead of studying isolated examples, astronomers can observe an entire sequence of worlds shaped by the same star and the same formational history, but differing in subtle ways. It's like conducting a controlled experiment where nature provides multiple samples under slightly varying conditions. The results constrain theories and eliminate hypotheses that can't explain the full range of observations. Water detection also opens pathways to studying other aspects of these planets. If water is present, other molecules likely are too. Webb can search for carbon dioxide, methane, ammonia, and even more complex organics. These molecules together paint a picture of atmospheric chemistry, revealing whether the atmospheres are oxidizing or reducing, whether chemical equilibrium dominates, or if active processes drive chemistry away from equilibrium. On Earth, biology disrupts chemical equilibrium. Oxygen accumulates because photosynthesis produces it faster than geological processes consume it. Methane persists because microbes generate it. If Webb detected similar disequilibrium signatures on an exoplanet, it would suggest active processes, possibly biological, maintaining the imbalance. While the planets in HD 110067 are unlikely to host life, studying their atmospheric chemistry prepares astronomers for analyzing more promising targets in the future. The technological achievement behind this discovery deserves recognition. Webb's instruments operate at the edge of what physics allows. Detecting water vapor on planets 150 light-years away requires collecting photons that have traveled for 150 years through the vacuum of space, passing through a thin shell of gas around a planet that blocks only a tiny fraction of starlight. The signal is faint, buried in noise from the star itself, scattered light from the telescope's optics, and radiation from the instrument detectors. Extracting meaningful data requires precise calibration, sophisticated algorithms, and painstaking analysis. Each transit observation lasts hours. The telescope must point at the target with extreme stability, holding its position to within a fraction of an arcsecond while the planet crosses the star. Any drift or vibration smears the signal and reduces sensitivity. Webb's sunshield, a structure the size of a tennis court, blocks heat and light from the sun, allowing the telescope's mirrors and instruments to cool to temperatures just a few degrees above absolute zero. This cold environment minimizes thermal noise, improving sensitivity to the faint infrared signals from distant planets. Data processing involves multiple stages. Raw detector images are corrected for instrumental effects, calibrated against standard sources, and combined to produce spectra. Atmospheric features are extracted by comparing spectra taken during transit to those taken before and after, when the planet is not blocking the star. The difference reveals the absorption caused by the planet's atmosphere. Statistical techniques assess the significance of detected features, ensuring that apparent signals aren't just random fluctuations. This process is rigorous, time-consuming, and essential. A single misinterpreted signal could lead to incorrect conclusions, wasting observing time and misleading the scientific community. The teams analyzing Webb data include experts in instrumentation, spectroscopy, atmospheric modeling, and statistics. Collaboration and peer review ensure that results are robust and reliable. The success of these observations has implications for future studies. Webb is booked years in advance, with astronomers competing for observing time to study everything from the earliest galaxies to planets in our own solar system. The HD 110067 discovery demonstrates that detailed atmospheric characterization is feasible for multiple planets in a single system. This opens opportunities for comparative planetology on an unprecedented scale. Other star systems with multiple transiting planets can be studied similarly, building a catalog of atmospheric compositions across a range of stellar types and planetary architectures. Over time, patterns will emerge. Certain types of planets might consistently show water vapor. Others might lack it. Stellar activity, planetary mass, and orbital distance will correlate with atmospheric properties in ways that reveal the physical processes at work. This empirical approach, grounded in observations rather than theory alone, will transform our understanding of planets and their atmospheres. Let's consider what these findings mean for the search for life beyond Earth. The detection of water on 5 planets doesn't indicate that life exists there. The planets are too hot, too irradiated, and too hostile for life as we know it. But the discovery shifts probabilities and expectations. If water is common, then one of the key ingredients for life is widespread. This increases the likelihood that somewhere in the galaxy, water exists on a planet where conditions are more favorable. The search for life focuses on planets in the habitable zone, the region around a star where temperatures allow liquid water to exist on the surface. For HD 110067, the habitable zone lies farther from the star than any of the planets studied. Webb hasn't observed planets in that zone, but the presence of water throughout the inner system suggests it could exist in the outer regions as well. Future observations might detect additional planets or characterize the outer planets in more detail. The concept of habitability itself is evolving. Traditional definitions focus on surface liquid water, but life might not require surface oceans. Moons like Europa and Enceladus in our solar system have subsurface oceans beneath thick ice crusts. These oceans are isolated from the surface but still provide environments where life could potentially exist. Similarly, exoplanets with thick atmospheres might have layers where temperature and pressure allow liquid water droplets to form, even if the surface is scorching hot. Detecting water vapor in an atmosphere doesn't tell you whether liquid water exists below, but it raises the possibility. Atmospheric models can estimate pressure and temperature profiles, identifying where conditions might permit liquid water. If those conditions exist, the planet becomes a candidate for further study, even if it doesn't fit traditional habitability criteria. Another consideration is the diversity of life. On Earth, life thrives in extreme environments: boiling hot springs, acidic lakes, deep ocean vents, frozen polar ice. Organisms called extremophiles demonstrate that life can adapt to conditions far outside the comfortable range humans experience. This adaptability suggests that life might arise in environments we consider hostile, provided basic requirements are met. Water is one of those requirements, but the specific temperature, pressure, and chemistry can vary widely. Exoplanets with water vapor might host life forms radically different from anything on Earth. Detecting such life would require identifying biosignatures, chemical or physical indicators of biological activity. On Earth, oxygen and methane together suggest life, because geology alone doesn't produce both in large quantities. Similar disequilibrium signatures on an exoplanet could hint at biology. Webb's spectrographs can search for these markers, though detecting them requires extremely sensitive observations and careful interpretation. The HD 110067 system isn't a target for biosignature searches. The planets are too extreme. But every detection of water, every characterization of an atmosphere, and every comparative study of multiple planets builds knowledge that will eventually guide the search for life. By understanding how atmospheres form, evolve, and respond to stellar radiation, scientists can predict which planets are most likely to be habitable. This predictive capability is essential because observing time on telescopes like Webb is precious. Targeting the right planets maximizes the chances of finding something significant. Looking ahead, the HD 110067 system will remain a focus of study. Webb's initial observations provided spectra during a few transits, but ongoing campaigns will observe additional transits, searching for temporal variability in water abundance. Variability could indicate weather patterns, seasonal changes, or responses to stellar flares. Each observation adds depth to our understanding, transforming static snapshots into dynamic portraits of active worlds. Other telescopes will contribute as well. Ground-based observatories can monitor the star for flares and magnetic activity, providing context for atmospheric observations. Future space missions designed specifically for exoplanet studies will target systems like HD 110067, using complementary techniques to probe different aspects of planetary environments. The European Space Agency's Ariel mission, planned for the 2030s, will conduct large-scale surveys of exoplanet atmospheres, characterizing hundreds of worlds across a range of types and conditions. HD 110067 will serve as a benchmark, a well-studied example against which other systems can be compared. The wealth of data available for this system makes it ideal for testing models, refining techniques, and training the next generation of astronomers. Universities and research institutions around the world are already incorporating these findings into curricula, teaching students how to analyze spectra, interpret atmospheric signals, and draw conclusions from complex data. The discovery also highlights the importance of international collaboration. Webb is a joint project involving NASA, the European Space Agency, and the Canadian Space Agency. Scientists from dozens of countries contributed to its design, construction, and operation. Data is shared openly, allowing researchers everywhere to participate in analysis and discovery. This collaborative model accelerates progress and ensures that diverse perspectives and expertise inform scientific conclusions. Public interest in the discovery has been substantial. Water on distant planets captures the imagination in ways that abstract astronomical phenomena sometimes don't. People understand water. They know its importance for life. The idea that water exists on 5 planets in a single star system feels both familiar and alien, grounding the cosmos in concepts everyone can relate to, while simultaneously expanding the scope of what's possible. Educational outreach programs have used the discovery to engage students and the general public in discussions about astronomy, planetary science, and the search for life. Planetariums and science museums feature exhibits explaining how Webb works, how scientists detect water on exoplanets, and what the findings mean for our understanding of the universe. These efforts inspire the next generation of scientists and foster public support for continued investment in space exploration. Media coverage has been extensive, with headlines around the world announcing the discovery. While some reporting oversimplified the findings or speculated about implications beyond what the data supports, overall, the coverage has been accurate and has conveyed the significance of the achievement. Scientists involved in the research have engaged with the media, providing interviews, writing articles, and using social media to explain the discovery in accessible terms. This transparency helps build trust and ensures that the public understands both what has been found and what remains unknown. The discovery also prompts reflection on the pace of progress in astronomy. A few decades ago, detecting exoplanets was itself a major achievement. The first confirmed exoplanet around a sun-like star was discovered in 1995. Since then, thousands of exoplanets have been found, and the field has advanced from simple detection to detailed characterization. This rapid progress is driven by technological innovation, improved instruments, and the dedication of researchers worldwide. Looking forward, the next decades promise even greater advances. Upcoming telescopes will have larger mirrors, more sensitive detectors, and capabilities Webb doesn't possess. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2000s, will survey vast regions of the sky, identifying thousands of new exoplanets. Ground-based extremely large telescopes with mirrors 30 meters or more in diameter will achieve resolutions and sensitivities that dwarf current capabilities. These instruments will study exoplanet atmospheres in unprecedented detail, detecting molecules present in trace amounts and identifying subtle features invisible to today's telescopes. The ultimate goal, of course, is to find definitive evidence of life beyond Earth. Whether life exists on exoplanets remains one of the most profound, unanswered questions in science. The detection of water on 5 planets in HD 110067 doesn't answer that question, but it demonstrates that the ingredients for life are not rare. Water, carbon, nitrogen, oxygen, and phosphorus, the essential elements of biology, are abundant in the universe. They form through nucleosynthesis in stars and are distributed through supernova explosions and stellar winds. Planets incorporate these elements during formation, and under the right conditions, chemistry becomes biochemistry. The transition from chemistry to life is not well understood. We know it happened on Earth, but we don't know how common it is elsewhere. Finding life on even one other world would transform our understanding of biology, evolution, and our place in the universe. It would demonstrate that life is not a unique accident, but a natural outcome of cosmic processes. Until that discovery is made, every step forward, every planet characterized, every molecule detected, builds the foundation necessary to recognize life when we find it. The HD 110067 discovery is one such step. It reveals that water is widespread, that planetary systems can retain volatiles over billions of years, and that our telescopes are capable of studying distant atmospheres in exquisite detail. Each of these revelations brings us closer to answering the question of whether we are alone. There are philosophical dimensions to this work as well. The realization that water exists on distant planets challenges our sense of Earth's uniqueness. For millennia, Earth was the only world we knew. The sky was a vault of lights, beautiful but unreachable. Now we know those lights are suns, many with planets, some with water, possibly with life. This knowledge reshapes our perspective, making the universe feel both larger and more familiar. It's larger because the scale of existence, the number of worlds, and the diversity of environments exceed anything our ancestors imagined. It's more familiar because the same molecules, the same physical laws, and the same processes that shaped Earth also shaped those distant worlds. This duality, vastness combined with familiarity, is central to modern astronomy. We are part of the universe, not separate from it. The atoms in our bodies were forged in stars. The water in our cells might have been delivered by comets billions of years ago. Understanding the cosmos is, in a sense, understanding ourselves and our origins. The study of exoplanets connects to these deep questions. By exploring other worlds, we learn about the processes that made Earth habitable. We discover whether our planet is typical or unusual, whether life is common or rare. These insights inform our choices about how we treat our own world. If Earth-like planets are abundant, then life might be as well. If they're rare, then Earth becomes even more precious. A fragile oasis in a largely barren cosmos. The HD 110067 discovery leans toward abundance. Water is not scarce. Planetary systems are not chaotic. The conditions necessary for complex chemistry exist throughout the galaxy. While this doesn't guarantee life, it suggests that the universe is not hostile to it. Returning to the technical aspects, the methods used to detect water on these planets will be applied to many other systems in the coming years. Transit spectroscopy. The technique Webb employed works best for planets that pass directly in front of their stars from our perspective. This geometric alignment is random, so only a small fraction of planetary systems are oriented correctly. However, the sheer number of known exoplanets means that hundreds or even thousands of systems are suitable for this method. Astronomers prioritize targets based on several factors: the star's brightness, the planet's size and orbital period, and the likelihood of detecting interesting atmospheric features. HD 110067 was an ideal target because the star is relatively bright, making it easier to collect photons and the planet's transit frequently, allowing multiple observations within a reasonable time frame. Other systems might require more observing time or more sensitive instruments, but the same basic approach applies. An alternative technique, direct imaging, involves blocking the star's light to photograph the planet directly. This method works best for planets that are far from their stars and orbit stars that are relatively dim. Imaging reveals the planet itself, not just its atmospheric absorption spectrum. Future telescopes with advanced coronagraphs or star shades will excel at direct imaging, complementing the transit spectroscopy approach. Combining methods provides a more complete picture. Transit spectroscopy reveals atmospheric composition. Direct imaging reveals the planet's brightness, color, and, in some cases, surface features or cloud patterns. Together, these techniques characterize planets in ways that no single method can achieve alone. The field of exoplanet science is still young, but it's maturing rapidly. The first generation of studies focused on detection and basic characterization. The current generation, exemplified by Webb, delves into atmospheric composition and chemistry. The next generation will search for biosignatures and explore the diversity of planetary environments. Each phase builds on the previous one, leveraging new technology and accumulated knowledge to ask deeper questions. The HD 110067 system will remain relevant throughout this progression. It serves as a laboratory for testing ideas, a benchmark for comparison, and a case study in how planetary systems form and evolve. As our understanding deepens, revisiting this system with more advanced instruments will reveal details invisible to Webb. Perhaps future observations will detect clouds, measure wind speeds, or identify rare molecules present in trace amounts. Each discovery will refine models and guide future research. There's also a human element to this work that deserves acknowledgement. Behind every discovery are people, scientists, engineers, technicians, and support staff who dedicated years or even decades to making it possible. Building Webb required international teams working across different time zones, languages, and cultures. Launching it involved precision, courage, and a tolerance for risk. Operating it demands vigilance, expertise, and the ability to respond to unexpected challenges. The success of the HD 110067 observations reflects the collective effort of thousands of individuals who contributed their skills and passion to advancing human knowledge. Their work is not always visible, but it's essential. Without their dedication, discoveries like this would not happen. Astronomy at its best is a collaborative endeavor driven by curiosity and the desire to understand the universe. The HD 110067 discovery exemplifies this spirit. It began with observations suggesting something unusual, continued with careful planning and execution of Webb observations, and culminated in the announcement of a finding that expands our understanding of planetary systems. The story doesn't end there. Each discovery raises new questions, prompting further observations, deeper analysis, and broader exploration. Science advances through this iterative process where answers lead to questions and questions lead to answers. The presence of water on 5 planets in one system is now established. What comes next? Do other systems show similar patterns? How does water abundance correlate with planetary properties? Can we detect liquid water, or are we limited to vapor and ice? What other molecules accompany water, and what do they reveal about atmospheric chemistry? These questions will occupy researchers for years, driving the next phase of exploration. The tools exist to pursue these questions. Webb is operational, producing data that will keep scientists busy for a decade or more. Other telescopes are being built or planned, each designed to push the boundaries of what we can observe. The challenge is no longer whether we can study distant atmospheres, but how deeply we can probe them and how much we can learn. Education and outreach will play critical roles in sustaining this effort. Public support for space exploration depends on engagement and understanding. When people appreciate the significance of discoveries like HD 110067, they're more likely to support funding for future missions. Scientists have a responsibility to communicate their work clearly, honestly, and enthusiastically, sharing both successes and setbacks, explaining not just what was found, but why it matters. The HD 110067 discovery offers a compelling narrative. Water, a molecule essential to life, exists on multiple planets around a distant star. This simple statement carries profound implications, inviting reflection on our place in the universe and the possibility of life beyond Earth. It's a story that resonates with people of all backgrounds, transcending technical jargon and academic boundaries. By sharing this story widely, scientists can inspire the next generation and build a culture that values exploration and discovery. There are also economic and strategic dimensions to consider. Space exploration drives technological innovation. The instruments developed for Webb have applications in medicine, communications, and other fields. The skills required to design, build, and operate space telescopes transfer to industries ranging from aerospace to software development. Investing in astronomy generates returns that extend far beyond scientific knowledge, contributing to economic growth and technological advancement. Nations that lead in space exploration gain prestige, influence, and strategic advantages. The ability to study distant planets demonstrates scientific and technical prowess, signaling capability and ambition. International collaborations like those behind Webb foster diplomacy and cooperation, building relationships that transcend political boundaries. The HD 110067 discovery is a testament to what humanity can achieve when we work together toward common goals. It's a reminder that despite our differences, we share a curiosity about the universe and a desire to understand our place within it. These shared values unite us and drive progress. As we look to the future, the discoveries made possible by Webb and its successors will continue to reshape our understanding of the cosmos. The detection of water on 5 planets in HD 110067 is just the beginning. Future observations will reveal more about these worlds, their atmospheres, and their histories. Other star systems will yield their secrets, expanding the catalog of known exoplanets and deepening our understanding of planetary diversity. One day, we may find a planet with an atmosphere that defies non-biological explanations, a world where chemistry has given rise to biology, where life has taken hold and flourished. That discovery, if it comes, will stand as one of humanity's greatest achievements. But even if we don't find life, the search itself is worthwhile. It teaches us about the universe, challenges our assumptions, and expands the boundaries of knowledge. It reminds us that we are explorers by nature, driven by curiosity and the desire to understand. The HD 110067 discovery is a chapter in this larger story, a milestone on the journey toward answering fundamental questions about existence, life, and the cosmos. Reflecting on the broader context, the ability to detect water on planets 150 light-years away represents a triumph of human ingenuity. A century ago, the existence of other planets was speculative. Now we study their atmospheres and measure their compositions. This progress is breathtaking, a testament to the power of science, technology, and human determination. It's easy to take such achievements for granted, to see them as inevitable outcomes of progress. But each discovery required vision, effort, and perseverance. The scientists who proposed Webb, the engineers who built it, and the astronomers who operate it are pioneers, pushing the boundaries of what's possible. Their work builds on centuries of accumulated knowledge, standing on the shoulders of giants who came before them. Newton, Einstein, Hubble, and countless others laid the foundations that make modern astronomy possible. Each generation adds to this foundation, constructing new edifices of knowledge that reach higher and see farther. The HD 110067 discovery is part of this continuum connecting past, present, and future in the ongoing quest to understand the universe. There's also a humbling aspect to these findings. The universe is vast, ancient, and indifferent to our existence. The planets around HD 110067 formed billions of years ago, long before humans walked the Earth. They've orbited their star through geological ages, their atmospheres evolving, their surfaces changing. We observe them now, briefly, capturing snapshots of their current state. What we see is a moment in their long histories, a glimpse of processes that have unfolded over timescales we can barely comprehend. This perspective reminds us of our own smallness. Earth is one planet among billions in the galaxy. Our entire history, from the first civilizations to the present day, is a blink in cosmic time. Yet here we are, capable of reaching across light years to study distant worlds, to measure molecules in their atmospheres, and to ponder our place in the grand scheme of existence. There's something profound in that capability, something that speaks to the uniqueness of consciousness and intelligence. The universe may be indifferent, but we are not. We observe, we question, we seek understanding. In doing so, we give meaning to the cosmos, imposing order and narrative on the chaos of existence. The HD 110067 discovery invites us to continue this quest. It shows that the universe is knowable, that its secrets can be uncovered through observation and reason. It demonstrates that the tools we've built and the methods we've developed are capable of revealing truths hidden across vast distances. And it suggests that the journey is far from over. Each answer leads to new questions, each discovery to new mysteries. This endless progression is what makes science so compelling. There is always more to learn, always deeper layers to explore. The detection of water on 5 planets in one star system is a significant achievement. It confirms that water is common in the galaxy, that planetary systems can retain volatiles over billions of years, and that our telescopes can study distant atmospheres in extraordinary detail. These findings reshape our understanding of planetary formation, atmospheric evolution, and the potential for life beyond Earth. They demonstrate the power of modern astronomy and the value of investing in space exploration. But beyond the technical accomplishments, the discovery resonates on a human level. It connects us to the cosmos, reminding us that we are part of something larger than ourselves. It inspires wonder, curiosity, and a sense of possibility. It encourages us to look up at the night sky and see not just distant points of light, but worlds, each with its own story, its own chemistry, and perhaps its own mysteries waiting to be uncovered. As we continue to explore, as we build new telescopes and develop new techniques, we move closer to answering questions that have occupied humanity for millennia. Are we alone? What is our place in the universe? How did life begin, and how common is it? The HD 110067 discovery doesn't answer these questions definitively, but it provides clues, evidence, and direction. It shows us where to look, what to measure, and how to interpret what we find. It's a step forward on a journey that has no clear endpoint, only milestones marking our progress. The universe is vast, and our knowledge is limited. But every discovery, every observation, every insight brings us closer to understanding. The presence of water on 5 planets in a distant star system is one such insight, a piece of the puzzle that makes the larger picture clearer. And as the picture comes into focus, we see not just the universe as it is, but ourselves as we are, curious, capable, and connected to the cosmos in ways we're only beginning to comprehend. If this exploration resonates with you, if the idea of water on distant worlds sparks your curiosity, then stay engaged. Follow the discoveries as they unfold. Support the missions that make them possible. And share the wonder with others, because the quest to understand the universe is a human endeavor, one that benefits from the widest possible participation. The stars are waiting, and the answers they hold are closer than ever before.